Well, we are going to start maybe a multiple episode series on thermodynamics. This one is kind of an overview of the whole field in a sense that we're going to touch upon some questions I think Zach and I both have about the field or had going into this because it's a rough topic to learn. I think it's one of my weaker things going through undergrad and grad school. I don't even think I touched it in grad school. So yeah, thermodynamics. What's your thoughts on thermodynamics?
Yeah, I did not. Well, let's see. I enjoyed thermo like when I took it. For those of you who don't take physics as a major, you're not a physics major. The way physics degrees work is you take the class once with like a certain level of math, like you learn all the physics with a certain level of math, and then that's the first 2 years. And the next 2 years you do it all again, but with a higher level of math. And then in grad school you do it all again, but with even different math and more. Mm-hmm. You kind of each time you peel off some of the assumptions and things you glossed over. So the first time I took it, those first 2 years, I actually enjoyed thermo, kind of learning about engines and stuff and PV diagrams. But then when I took stat mech, I don't know if it was just who I took it with or what, but it nothing ever really stuck together. It didn't build a picture for me. Like the idea when I took the course too, and I think this is not everyone takes this approach, but like historically thermodynamics came first and then stat mech was like came afterwards. But my professor was like, okay, we're going to flip it. We're going to teach you stat mech because from stat mech you can derive thermodynamics. So you build up to it. So we did stat mech first, and I don't know. It just nothing. It never built to thermodynamics for me. Like it never made the clearest sense.
Yeah, I think part of the problem. I was thinking about other fields of physics that you learn, and yeah, you said it right. You learn thermo in freshman year, your first year physics major classes, maybe sophomore year. You learn thermo. You don't really touch stat mech in those classes. It's like maybe mentioned when they talk about entropy, but it's very much like one page and like one problem at the back of the book, and then you move on. But most of the emphasis is like engines and efficiency and like that kind of stuff. Yeah. I mean, maybe chemists more than engineers, but like engineers in like turn of the 1900th century, like engineers who are like doing engine type work, like on like trains or maybe. But so other fields like classical mechanics, all the ones I could think of were really well polished by one person's brain. Like Newton polished mechanics, even though there was stuff before Newton, he really, obviously added a lot to it, but it's his foundation that we built all of mechanics on. Maxwell with electricity and magnetism polished all of that into one person saying, here's the concepts we need to focus on. He's the source of a lot of the labeling of things like the magnetic field being B, like, all the conventions that we use for E&M. Maxwell gave us that. And he polished other people's stuff like Faraday, but compiled it into a nice package. Relativity, obviously Einstein, it came from his brain, pulling some stuff from different math places and some Lorentz stuff, but it's his like work that we are studying when we learn relativity. Quantum mechanics is an interesting one. It was pretty well established, but I think we could point to von Neumann as like the guy who polished quantum mechanics for us and gave us the foundation that we use now in the 20s after it had been around for like 15 or 20 or so years. So each case, I think we have a clear single individual who just did cleanup on the topic. But thermo, there isn't that. There isn't somebody who came through and like cleaned up thermodynamics. So we're kind of stuck with this disjointed field that relies a lot on like chemistry experiments, but then there's some like heavy math underlying it that we haven't really reconciled. Well, people who are good physicists and like actually study this stuff at like an advanced level totally get this. I'm saying the junior, senior, undergrad level physics, thermodynamics is rough. And you learn stat mech alongside it. And it's like underneath classical mechanics is quantum mechanics. but it's a pretty big gap between those two things. But underneath thermodynamics is stat mech, and it's close enough that thermo kind of gets brushed aside in grad school and you learn stat mech. A lot of emphasis on stat mech principles, less so on thermo in grad school. There's not much. Maybe if you start getting into black holes, the like entropy thermodynamics of black holes starts getting important in grad school, but like heat engines, no one touches really in grad school. There's not like a class where you're like, oh, it's very important to know the enthalpy of, I don't know what, this trying to think of an example of something I did in grad school. This like field, like that's basically what you're doing in grad school is a lot of like pre QFT work, and like thermo's just not there. So that's my summary of why thermo is so bad, basically, is like it's a mix of 1800s experiments and like advanced differential geometry topology stuff underlying it that we just didn't have the vocabulary for or the framework for when it was being developed. And it hasn't really been reconciled in a nice, neat package yet.
Yeah, I think...
I don't think it will.
And I don't know if stat mech, like if this problem necessarily is leading to also a problem in thermo, an understanding in thermo, at least in undergrad. But I think you and I both talked about this once, how like I kind of feel like at least my professor, I feel like did not at least teach stat mech very well. Maybe I might go so far as to say is like I'm not sure he had the best stat mech grasp. And I think I have a theory out there that no one really understands it because of this exact same problem. So like if I were to go on and teach, I would teach stat mech at the level that I know it, which is not good because my professor didn't know it and his professor probably didn't know it. And I think just nobody knows it really. Yeah, which is not true. There are people that really understand it, but
yeah,
totally. Maybe they don't teach. I don't know.
Yeah. I hated stat mech and I didn't get it like at all. And there's a lot of vocab that doesn't make sense and it's very confusing at the like junior level undergrad class that you're taking in thermo. And maybe that's sophomore year. I don't know. But yeah. And then you see stat mech again in grad school and it clicked a hell of a lot more in grad school. But I did have like, I took it twice. And not because I failed, but because I went for a master's at one school and then a PhD in another, and I just retook it. And the teacher I had the first time was not great, but I was at a stage in like my educational abilities where I went to the library and checked out like 5 books on stat mech and was like, okay, here's what my teacher is saying. I'm going to read a whole bunch of books on the same topics and compile like my understanding and like reconcile what the teacher's saying with like what other books say. And that helped a lot. And it was probably like one of the first times I'd really like pushed myself in like a course academically like that. And I can promise you it helped a lot. So, and I think that was maybe one of the first times where it was like, oh, this is how you learn. Like up until then, it was kind of like skating through, doing some homework problems as you do as an undergrad and then taking a test and be like, cool, got it. I got a B or an A and I'm good. But then stat mech, I like really pushed myself to do the independently learn stuff and like do the work to figure it out. And it worked. It totally worked. And I totally got a better grasp of stat mech. And yeah. So when you go to grad school, you take qualifying exams for those that are going to get into that. 1 exam per topic, basically. And stat mech was the only one I passed on the first try, which is pretty rare. Like most people, you take them just to see what you pass. And then you take the ones you didn't pass the next time. And you get like 3 tries. And stat mech was the one that was the when I got done right off the bat. But I still took the class again because I was like, I know I passed this, but I think I would benefit by seeing it one more time at the new school. So yeah, I like stat mech. Stat mech makes more sense to me than thermo.
So one small anecdote I have thermo related is I don't know if I've said this on the podcast or not before, but I have a hobby of taking my photo with dead scientists, dead physicists. Not their actual bodies, but their grave sites. So I've kind of
I thought it was something even worse, where you take a picture with scientists and then they die.
No, I'm not like the rig or anything. No, so like when I went to Europe in 2015, like I went to a lot of different graveyards, and like I found outside of Austria is Boltzmann, for instance. He's got a great bust on his tombstone. And one of the best places to go to do this actually is I forget what the French name of it is, but I think it's called like the Hall of Heroes. Is it the Pantheon? Maybe I think it's the Pantheon, where it's in Paris, and instead of it being a like religious, it used to be a religious building. I'm sure it was cross shaped, but I think it was like where the Greeks would like go to talk to their gods and put their statues of their gods and stuff. Well, then the enlightened French, they said, no, screw that. We're going to put all of our famous scientists there. And so that's what they did. So buried there is, Marie Curie, Pierre Curie. I think Lagrange is there. Just a lot of people you'd know. And when I was there, I happened to notice, there's Carnot back there. And but it was in like kind of a place where I couldn't get to, so I kind of had to take it from a distance a little bit. I couldn't fully read it, so I took my picture with Carnot's tomb, and then I later looked it up, and I realized, oh no, there's actually a couple Carnots, and this was a Carnot that like worked for Napoleon and like wasn't really a great guy, but was not the Carnot of the Carnot cycle. And I was like, dang it, I missed it. I was like right there because must have been like one of the other Carnots that were right there. I just happened to get the wrong one. Yeah, and I was in in the basement of a giant building, so I didn't have service to like look.
You're like, I'm sure this is the right guy.
Yeah.
Probably not.
Yeah. Nope. Okay, it was the wrong Carnot.
Yeah. So the thermo. I'll just add one last thing. The teacher I had at UC Santa Cruz, which is where I took the last StatMech class I took in grad school, totally understood StatMech at a different level than anyone I heard talk about StatMech, and it was fantastic. So thank you to that teacher. Kind of like, I shouldn't say this because it's hard to compare, but like a Feynman-esque grasp of StatMech, which was really insightful and interesting to learn from. So that was a cool class. So I think I kind of hinted at this, that there's really deeper underlying math principles at work. And I don't even want to talk about the laws of thermo because they're kind of not important, even though they're totally important. It's like they're so important, they're not important. They like wrap back around to being like, yeah, duh. So like the 0th law, I mean, they say that it like, they had to fix something in thermo and like redefine temperature first as the 0th law before they could talk about the first. Maybe, I don't know. Ostensibly the first or the 0th law defines temperature, and then thermo is built on that, which kind of makes sense. But
can you remind me, what is the 0th law? It's the two bodies that touch come to equilibrium.
It's like when two objects are in thermal equilibrium, that is the point where the temperatures of them are the same. That's like, they just fixed temperature being the thing that's the same when two objects are in thermal equilibrium. That's the 0th law. And then I'm going to skip to the 3rd law, which is also not important because it never comes up and doesn't affect anything, I don't think, as far as I can tell. 3rd law says you can't reach absolute zero, or the entropy goes to zero as the temperature goes to absolute zero. Different way to think of it. Again, doesn't come up, doesn't affect things. It's just kind of like a limiting case to thermodynamics, I guess. But it's not like the 3rd law of mechanics, like Newton's 3rd law, where we're like, great, I get it. Conservation of momentum. This has big, important practical implications and helps me solve problems. Like the 3rd law of thermo doesn't do that. And then you can even argue the 1st law, which is essentially conservation of energy, just applied to like thermo systems. We already have conservation of energy. It's like pretty established before we get to thermo. So why do we need another reiteration of it? But I guess, there's like mathematical versions of it, but underlying it is the law of conservation of energy, which we already got covered. So we jumped from 0 to 3 to 1, and then number 2 is the one that's like the new one that actually comes into play in thermo, which is the kind of conservation of entropy. Like it can only go up in the universe. It can't decrease. So Yeah, that's our laws of thermo that underlie everything, with two of the four being not super important.
So yeah, I totally remember this 100%. But for the listener out there who doesn't remember though, can you reiterate the first law?
I mean, I just said conservation energy,
Yeah.
but the mathematical form is du, or whatever. Energy is a combination of work and heat is one way to think of it.
Oh, okay, all right.
There's even problems with that, but yeah, that's usually how it's talked about. Is the change in energy is dependent upon the amount of work done on the system and the heat exchanged across the boundary of the system. So one of the things that cleared up thermo a lot for me was a website by, I don't know his name, but somebody who compiled a website. It's kind of like the Feynman lectures, but in like HTML form, and it's very all encompassing of lots of different fields of physics. The website is av8n.com.
Oh yeah, I remember you telling me about this.
Yeah. I feel like it's a little secret. I don't know how I found it, but I found it a while ago, and everything I've read from this site has been spot on and really helpful. A very opinionated person who has thoughts on physics in a very good way, meaning he like clears up a lot of misconceptions, and it's like he thinks a lot about pedagogy and like how things are taught, and so but to almost to a fault where he's making claims like the word heat shouldn't even be used, which fair, because it's a confusing concept in thermo that you read about and you're kind of like, wait, why is it like this? And he's just like, get rid of that word. Don't even use the word heat. If you see heat, replace it with TDS, temperature times infinitesimal amount of entropy. Just like heat can mean lots of different things in different situations. We should just get rid of it and then use whatever version of that word we're using at that time.
And just to credit the person, I believe it's John, I just went to the website, so it's John S. Denker, Denker.
Cool. Yeah, he's a pilot, I think, or somehow aviation guy, which is the reason for his website being named Aviatin. He has a cool part of his website about how flying works.
Yeah, that's the big thing on it right now. See how it flies.
Yeah, but you can dig into like his physics writing, which is interesting. And he's not like a outsider quack guy who like just comes up with weird theories. Like he has a lot of published work in particle physics experiments and stuff like that from like the 80s. He's been around for a long time and he knows what he's talking about. So yeah, he has a lot of discussion of thermodynamics and pulls in good references and has good diagrams, and it's dense but readable, and it's somewhere between undergrad lecture notes and like published academic papers. It's very similar to Feynman lectures. It's like, if you know what he's talking about, it's a really cool like overview and like clean up fix of like stuff you learned. As a first introduction to it, it's probably not the best because it kind of assumes you know some stuff already. Very similar to Feynman. So he talks a lot about the laws as I explain them, namely that the 0th doesn't matter, the 3rd doesn't matter, the 1st we already have, 2nd is kind of the new thing, and that's it. But when you learn thermodynamics, you're probably doing a lot of like heat from a heat bath, which is like just a massive body like the ocean that could exchange heat with something without changing its own temperature. And then that heats something up or cools something down, and then it's probably a gas in some chamber, and the pressure and the volume changes. So all of that to say, when you're doing thermodynamics, you have to keep track of lots and lots and lots of variables all at the same time. So I think that right there is the first hiccup that people learning thermo hit, is that they're used to like f of x, or like, how position changes with time, like one thing dependent on one other thing,
right?
Or like XY coordinates, like 2-dimensional kinematics or something, where things are nice and rectangular and there's just this one independent variable that's affecting other things that are functions of that variable. But thermo is like, throw all that out the window. You have at least 5, probably more, usually more variables that are all changing at the same time, that are not independent. They're dependent on each other. You have this like multi-dimensional space and you're trying to do like surface integration on stuff without realizing that's what you're doing. And it just gets messy real fast because people do like hand wavy explanations and reasonings for equations that come in and out of existence that don't seem to make sense or fit what you're talking about, which is like a bottle of gas, basically. And it gets messy real fast.
Yeah.
Like real fast. So yeah, the first law of thermo, you can talk about the energy of a system being dependent on things like the temperature, the entropy, the pressure, the volume, the number of particles, and then you have these variables, and they're all changing all at the same time, and they depend on each other. The way we organize them is kind of nice, though, is we usually talk about pairs of variables. And the way we usually write it is that energy is equal to pairs of variables multiplied together. So like temperature times entropy.
Right.
And then pressure times volume. And sometimes we split those up into like heat and work. We give those like clumps of things definitions. But then there's other stuff that affects the energy of the system that might not be those variables, like the chemical potential and the number of particles, which is another pair of products. But I wanted to talk about that pair because learning what the pairs are, meaning like how do you know they go together and what do they do when you start changing things, helps you like answer what we're going to get to, which is a confusion you and I both have about thermo, which is like the other things that kind of look like energy, namely enthalpy and like that kind of stuff. So one thing to remember about thermodynamic systems and problems and situations is the difference between extensive and intensive variables, parameters. So these aren't necessarily extensive, intensive, but this is an example of something you might be familiar with that has a very similar like way of conceptualizing, which is the heat capacity versus the specific heat capacity. Like that was pretty well established in my brain going through thermo. Do you agree?
Not off the top of my head. So I know that like, I couldn't tell you the difference between the specific heat capacity and heat capacity.
So the specific heat capacity is the amount of energy to change the glass of the stuff you're holding in your hands. Like this exact system, how much energy does it take to change its temperature?
Okay.
The heat capacity, not specific. So specific is about the specific thing I'm holding in my hand. The heat capacity is how much energy does it take to change some amount of the material that you're holding. So not the specific sample that you're holding in your hand, but just like per kilogram of the stuff. Sure. So like that's like the amount of energy it takes to change the temperature of copper versus the amount of energy it takes to change the copper wire that I'm holding in my hand right now. Yeah. Like that's specific to that one bit of wire. Whereas the heat capacity is like specific. I shouldn't say specific. Heat capacity is the amount of energy it takes to change copper in general. So you can do it for whatever copper sample you have. Copper has a heat capacity. But the exact wire you're holding is a specific heat capacity.
So presumably there's some relation between heat capacity and getting to the specific heat capacity by looking at, I don't know, the volume or the mass or something like that.
Yeah. And the way we usually say it is the extensive variables depend on the number of particles, depend on the size of the system, meaning like number of particles, number of moles, any way you want to define like the amount of stuff you have. Those are extensive variables. Things like the volume, clearly, right? Like you could double the amount of stuff, it's going to double in size. If you had a block of copper and you're like, I want twice as much copper, the volume has now doubled. That's an extensive property. Intensive properties are things like temperature. If you had copper at 70 degrees Fahrenheit and you doubled the amount of copper all of a sudden, it's going to be 70 degrees Fahrenheit. It's just like that. The doubling of it doesn't make more copper doesn't mean necessarily that the temperature goes up.
Right.
I'm not talking about like adding particles to increase the pressure and like, heating something up by like pumping it up. I'm saying just like snap your fingers, all of a sudden you have more of it. The temperature is not changed. It doesn't depend on the amount of stuff you have.
Gotcha.
So those are extensive versus intensive. Temperature would be intensive. Okay, all of that to say, energy from thermodynamics is an addition of a whole bunch of pairs of extensive and intensive variables. So we usually say energy is temperature times entropy, and then add it to that, or I'm going to say subtract, and I'll explain why in a second. Pressure times volume. So those are intensive times extensive pairs. And then chemical potential times the number of particles. You can have other stuff like there's like, I mean, you could work in electromagnetism into thermodynamics and talk about like charge and flux and like stuff like that. But
so just really quickly,
potential, yeah.
So I want to verify I'm still following. Okay, so you're saying each of these pairs of products that we typically multiply together, one is an extensive and one is an intensive.
Mm-hmm.
One, but okay, so but wouldn't you said P and V, right? That's one of the simpler ones that we talk about. Isn't pressure an extensive variable? Doesn't it depend on?
It's considered an intensive variable. Yeah. If imagine changing the amount of number of particles in a gas.
Yeah.
And I think we have to just, maybe it's better to think of it this way. My guess is you're getting tripped up somewhere that I'm probably getting tripped up to, which is considering the gas inside of a sealed box. But then look in your room right now and imagine the air like in front of you, like count an Avogadro's number of gas particles and then count 2 Avogadro's number of gas particles. It's the same pressure, but the volume of that doubled.
Right. Okay. Yeah.
So you're considering like twice as many particles, but the pressure of that now doubled sample isn't bigger because you included more particles.
Yeah, and I think you can. I always imagine pressure too from kind of the stat mech area where it's like a billiard ball hitting on something with a certain energy. It imparts some force and you get averaged over all that. So I think if you just think of it that way too, if you add particles to it and you're just throwing more particles, but they all have the same energy, it wouldn't change the pressure, I don't think. So
yeah,
I mean maybe that's not the best explanation, but
no, so that's where the like stat mech touches the thermo, where like you consider the little individual atoms and particles, molecules bouncing around. That's the stat mech interpretation. The thermo is like the macro, just like what's happening to like this collection of an Avogadro's number of atoms. Okay, so let's stick with just the entropy, temperature, volume, and pressure stuff variables because it can get out of hand. But know that there are other ones. But those pairs of particles, when we start looking at how much does energy change when we change those variables, we usually start with the energy, the amount of energy changing, dE, like a differential d, is equal to T ds minus P dV. So those are that's like the definition of a change in entropy. The minus, by the way, gets the minus of P and V. That comes from whatever definition of work you want to pick. So it doesn't have to be minus P dV, but usually we talk about work being done on the system in such a way that if the volume shrinks, that's an increase in energy, like we're squeezing it. So like the negative change in volume is an increase in energy. So we have to throw in a minus sign there to make that taken into account.
Is this is one of those issues where it's like done on the system or done by the system?
Yeah.
I hate that. That was one of the, I think different authors will pick different conventions for that. And so, as you read across books, you have to like change your perspective from like the gas's perspective or the system's perspective to someone outside. Yeah. And that right. Also makes this confusing.
Yes. Yeah. It's not the first time that like the definition of the system and like what's happening is important, but it's the first time you can get really easily tripped up because in Newton's laws, when you're solving mechanics problems, it's kind of easy to be like, oh, I'm considering this block. This is the thing I'm paying attention to. And it's kind of simple to keep track of stuff. But like this gets weird when pistons are moving like what's doing the work? Is it the gas itself, or is it like the squeezing? So yeah. So just to say, the convention we're using for this, I'll stick with, is that it's minus PDV.
Okay.
Thinking about like a negative change in volume leads to an increase, a positive change in energy. Okay, so focus on where the D's are in that differential infinitesimal amount of energy, dE. It's T times ds minus P times dV. So that's like the amount of energy that's changing when something's happening. If we were to do an experiment with a gas or a solution or something, a chemical experiment, where we wanted to keep entropy and volume constant. So we're analyzing some system at constant entropy and volume, then the energy itself wouldn't change because ds is 0, dv is 0. So it's like saying the energy of the system is constant.
Right.
If we keep entropy and volume constant. So that's one way to think about just change in energy. But sometimes it's hard to keep entropy constant and volume constant at the same time. So sometimes we'll want to do things like keep entropy constant, but keep pressure constant instead, which might be an easier experiment to set up in a chemistry lab or something like that. So we wouldn't want to keep track of energy because energy would be changing if the volume changes. We want to keep track of something else, meaning when I say keep track of, we want something that doesn't change because that's easy to keep track of. We're just like, okay, we're doing an experiment where this value of this thing is not going to change. We can do a nice experiment because this thing is conserved within our system. We don't have to worry about it crossing the boundary of our system. So instead of looking at dV, it would be nice if we could change what gets the little d, the infinitesimal change, from the V to the P, to the pressure. So we want something that's like TDS minus VdP or plus VdP instead of PDV. So there's a nice little mathematical transformation. If you look in like a math textbook for scientists and engineers like Boas, did you use Boas?
I did. Yep.
Yeah, but Boas is awesome. If you're going through undergrad and have a mathematical physics engineer class, you might not use Boas, but I recommend picking up Boas just because it is really simple to learn from. And I always go back to it as like a reference.
Yeah, I was going to say, learning from it, I feel like honestly, it's maybe not the best
That could be true.
to learn from because it's a lot of like, here's this chunk, here's that chunk, here's this chunk. But going back when you know all those chunks like a little bit and you want to review it, it's perfect for that. It's so good.
Exactly. So in Boas, she has a section on the partial derivatives chapter, which is what we're doing here. We're taking differentials of some functions with respect to different variables when other variables are held constant and all that stuff. But there's a transformation to switch which variable gets the differential. So you can swap the P and the V, like change PdV to VdP. And it's our Legendre transformation. That's what we're doing in thermodynamics when we're changing the variables. So if you go into a math book and learn about the Legendre transformations, thermo is the big application of it. Another place you might see it is when you get into Hamiltonian mechanics, building that from your Lagrangian, that kind of stuff, where you change like from position and momentum position and velocity to position and momentum.
Yeah.
There's a little change of variables there. Yeah. So there's like underlying math that is the same for both Hamiltonian mechanics and thermodynamics, which is like partial derivatives with respect to one variable, but you want to change it to a different variable. So the way to do it is take E, the thing that you used to take a differential of, the thing you're previously considering, and subtract out the thing you want to change. So in our example, we want to swap P and V. So you take E and subtract PV. You actually subtract negative PB because we have the negative sign in the equation. So technically in this example, you add PV. So you have energy plus PV. That's a new function that we're just making up out of the blue.
No D's in the PV. Just
no D's in the PV yet. So we're just working with E plus PV. Now, if we do like the full differential of that gives us a new quote unquote first law for this new function that we just made up, E plus PV. And what happens if you work through the like chain rule for differentials? Sorry, I guess chain rule, but product rule for the differentials of that new function. You get TDS still hanging around, but you get a minus PDV plus PDV, and those cancel. And then you get a plus VDP as well. So that's the long way of the Legendre transformation that changes DE into D of E plus PV.
Okay.
And then what ended up happening on the right side is the D switches from the V to the P. The infinitesimal change volume has now changed into an infinitesimal change of pressure.
Right. So we have this new equation. Let me see if I can just say it back to you really quick. It's D of E plus PV. Of is maybe not the right word, but D and then the quantity E plus PV.
Right.
And that's equal to TDS, temperature times the differential of entropy, plus VDP.
That's right.
Okay. Yeah, I see how that all works out.
Yeah, by doing that little change of variable kind of switcheroo thing, we've invented a new function and we've switched the thing that is changing from volume to pressure. So the thing that is E plus PV, the thing that we had to invent to make that change of variable happen, that is what we call enthalpy.
Which is normally denoted like what, delta E or something?
It's
or
H.
U. H. There we go.
H. Yeah, enthalpy is H. Clearly, obviously, right? Yeah. I'm not even going to say the other words because it's so confusing every time. But yes, H is enthalpy.
I can imagine it because they said, okay, we can't use E. Obviously, we're already using E. So we'll go to the next letter. Oh, that's a T. Oh, crap. Can't use T either. What's the next letter? H.
Yeah.
Okay. Oh, I guess I skipped N. Oh, well, N's used too. So perfect.
Yeah. Yeah. H is enthalpy. It's not heat, which is Q.
Oh, that's a good point. Okay.
Yeah. But yeah, H is enthalpy. And the reason enthalpy is important is for chemists, basically. It's because chemical experiments, they want to analyze things like the spontaneity of like mixing stuff or like some reaction or the reversibility at stuff. And they want to do that at constant blank and blank. And entropy and pressure are two things that are easy to control to make constant in a chemical experiment. And so they can track enthalpy and talk about the conservation of enthalpy in a reaction and control it and build tables of the enthalpies of reactions in certain situations. Because they can look at the pressure and the entropy as being the things that are quote unquote changing. So you can think about like a chemical reaction and look up in a table. Okay, I have this much of this. I have this much of whatever oxygen gas, this much of hydrogen gas. What happens if I mix those things? Cool. It's going to release this much enthalpy,
which is a form of energy.
Yeah, it all has units of joules, and it's all, like joules per mole. That kind of stuff is what you'd find in a table.
So let me see if I can think about it. So, because it'd be like, okay, I have, I was going to say hydrogen and oxygen. That's not a good one. I don't know. We have an acid and a base, and I mix them together. Well, yeah, okay. Generally speaking, in chemistry, the volume stays constant during most reactions. So before measuring the energy, the dV part would be 0, and maybe that's an issue. So, but now we have, if we're measuring enthalpy, V is constant. That's fine, and pressure is maybe changing. I mean, I guess.
I think instead of thinking about the volume changing, the volume staying the same, I don't think it does. Imagine a result of a chemical reaction being a gas that's like outgassing from the liquids. And then all of a sudden you have a big expansion in volume. So that volume change happens and it's big. So you can think of like sealing something that's like in an expandable enclosure. And as the volume expands, it like expands perfectly to keep the pressure the same. So like it doesn't build up pressure inside a container. Something like that is maybe a way to think of it.
Wait, so we want the differential components to be zero? Is that
Yes.
okay?
Because then the quantity itself is constant.
Gotcha.
The differential of the thing itself is zero. So that's like enthalpy
I
is
see.
conserved,
Right. Yeah.
is the way to think of it.
Yeah. Yeah. If the differential is zero, then it's the
Thing itself.
Yeah, it's always constant. Gotcha.
Yeah.
Okay.
And then I had mixed it up when I started talking about looking up in tables, like how much enthalpy is released in the chemical reaction. That's a situation where it's not, dP is not zero. So that would be a release of enthalpy, where enthalpy is not constant.
Gotcha.
But chemists do reactions and calculate the enthalpy that they get by looking at the change in pressure, and then they could get a number for the enthalpy,
Gotcha. So
how much it changed.
So they just they have a pressure gauge. I'm very tactile, so I want to think about it a little bit. They got a pressure gauge, a grad cylinder, and a thermometer in there, and they can measure at least those ones. I don't know how you measure the change in
The
entropy.
Yeah. I think you have proxies for that, but yeah.
But then so you look at all those things, put it in an Excel spreadsheet, let's say, and then you get out the enthalpy. Just like, if you wanted to measure the kinetic energy of a ball, you have to look at its mass and look at its velocity, and then put those together, and you get a new thing called energy.
Right.
Okay.
Yeah. Yeah. So all of that was a big, long explanation of a change of variables from like energy being dependent on volume and entropy. And then if we want to swap it to pressure instead of volume, you do that change of variables, subtracting out or adding the quantity PV to energy. And then you end up with a new thing called enthalpy. So then what functionally happened mathematically is the differential swapped from the V to the P.
So in theory, if we want, I'm sure maybe this is where you're going, we can do the same thing with if we want to swap from ds to dt.
Exactly. That's exactly right. So the other kinds of functions that are energy-like that get confusing are the other ones, where let's keep minus PdV, but let's swap from TdS to SDT. So you can imagine the way you do that. You take your energy, the original function, but we're going to subtract from it T times S, and then work out the full differential of that thing. And the TdS, you have a TdS from the original function, and then you minus TdS to cancel that one out. But then you have a minus SDT floating around from the full differential of that product, from the product rule. So our old function E changed to E minus TS. And just a reminder, last time we had E plus PV. The plus was because we had a minus originally from our definition of how work is done. But this time, the general Legendre transformation is the original function minus the product of the variables you want to swap. So E minus TS leads to a new function. And that function is free energy. It's the free energy, which has nothing to do with the amount of energy available to do something, although some people try and say it is. But yeah.
Is it anyone's free energy or just free energy?
It's the term used for E minus TS is called free energy.
Okay. And is that F? Is that what
F, yes. The symbol is F. And I'm going to throw in a word that's going to make it confusing because it sounds like it should go with enthalpy, but it doesn't. It's Helmholtz free energy.
Oh, there we go. That's what I was wondering if it was. Yeah, it was somebody's.
Yeah. So Helmholtz free energy. The Helmholtz name is not the important part. The F free,
free
is the symbol, not force, but free energy.
Yeah, this is why this topic is so confusing too. It's I mean, I don't know who decided to use the words entropy, energy, enthalpy, and free energy.
We got free enthalpy coming up, so don't worry. We got canonical ensembles, grand canonical ensembles. Yeah, fun stuff. F, free energy, Helmholtz free energy, if you'd like. It changes the variable from entropy being the thing that's changing to temperature. Or, I mean, not changing. We want to hold it constant. So for chemists doing experiments, calculating things, having something that's a constant free energy is when you would have constant temperature and constant volume, which is reasonable. It's a reasonable experiment to run. You can imagine something that holds constant temperature and constant volume, just a liquid, right?
Yeah.
Combining liquids and keep a heat bath or ice bath around to keep the temperature the same. So that's free energy, which is another Legendre transformation of the energy of the system with a minus TDS.
All right. So yeah, we're building it up, and then I guess I don't know if you're going
just to highlight real quick before we leave free energy. It's minus TDS minus PDV. We got two minus signs in the free energy.
Gotcha.
The differential free energy, DF.
Gotcha. So I guess potentially where we're going here is, I think, well, you can tell me where I'm wrong, but it seems like right now, at least, we're out of variables, unless we want to start combining H's and F's. But I guess we have one more, right? We could swap it on both. Is that where we're going?
Yep, that's the next one.
But then eventually, I don't know if we're going to talk about that here. Like you were saying earlier, there's all these pairs of things that are roughly energy, or are energy. So far we've only talked about temperature, entropy, pressure, and volume. But there are, like you were saying earlier, like enthalpy, or was it no? What was the number of particles and
chemical potential?
Chemical potential. There we go. Thank you. Other ones that you may want to add. So you could play this game, and create a giant array of other things here.
So exactly. And let's round out right now we have 5 variables, just to keep track. We have energy, we have temperature, entropy, and we have pressure, volume. So that's 5. We could solve that function for entropy and make entropy the thing that equals the other pairs. And we're just going to have energy divided by temperature, pressure divided by temperature as the other terms, and come up with new names for that stuff. Basically, I'm trying to say energy is not magic as the one standalone thing. We could just use algebra to rearrange our functions to solve for the other one and do the same kind of stuff.
All right,
same math. It's not like any of them are particularly extra important. But usually we talk about energy equaling the other stuff, but we could solve it for one of the other stuff. And then energy is just floating around as part of a pair.
Gotcha.
Another way to think of it is energy's pair. Energy's, what would you say? Energy intensive or extensive? Pop quiz.
Oh, gosh. It depends on the number of particles, or it doesn't. I don't know. My brain wants to say it's extensive, but
extensive, right? Yeah, I think so. And I think you could think of it like you were saying with StatMech, like the little billiard balls flying around. The amount of energy that those billiard balls carry, if you double the number of billiard balls, your energy goes up, right?
Yeah.
That's one way to think of it. So yeah, energy is extensive. And you could imagine the intensive, you can make it up. The intensive pair is the number 1, if you wanted to, which is weird. But yeah, that's a way to just get pairs of stuff, even though it feels like you don't. Okay, so yeah, if we swapped both TDS and PDV to SDT and VDP, so we have both of them now flipped. It's kind of like do a Legendre transformation once and then do it again for the other pair. You end up with the last one, which is the free enthalpy, sometimes called the Gibbs free enthalpy, and unfortunately sometimes misnamed free energy, the Gibbs free energy. Some books talk about it like that, which is why it's also confusing.
That's what I've heard it as, is Gibbs free energy. So, but
Gibbs free energy. Yeah, technically, I think it's an enthalpy. Why? I'm not sure.
Yeah. So what's the difference between an enthalpy and an energy?
My reading of enthalpy is it's when you subtract TS from things. So if you have something and then you subtract TS from it, it's now an enthalpy.
Gotcha.
And so I think you take the free energy function and you subtract. Well, so free energy function F. Yeah, the enthalpy is E plus PV. Sorry, not TS. See, I'm already mixing it up. And I just read all this stuff and had it nicely organized. I'm looking at my handwritten notes. I'm still messing it up. Yeah. Energy E. Enthalpy E plus PV. Free energy E minus TS. So I guess you could think of enthalpy things are when you add PV to them.
Gotcha.
So take your free energy, which is E minus TS, and then add PV. It's now become an enthalpy because you added PV.
Gotcha. And we normally denote this by G, correct? Is that right?
Yes. For Gibbs, if you want to give it a name. Gibbs, by the way, was probably one of the closest people to polish up thermodynamics, but never happened completely. Some of the early quantum mechanics folks were like on the tail end of thermodynamics work. And like Planck, for example, talks about Gibbs very highly. It says Gibbs was probably one of the smartest people ever to live, as far as he was concerned.
Yeah, I think that's like one thing I've heard about like kind of the stat mech and thermo world was that we were doing a lot of great work on it, and then quantum came and we're like, this is more interesting. Mm-hmm. And like as a collective group of physicists, we just abandoned ship and went to the more interesting thing.
Yeah, we got distracted away from thermo before it could totally be polished.
Yeah,
exactly. Yep. I mean, Planck was basically doing thermo when he had to do the quantum,
right? Yeah,
the quantum switcheroo. Okay, so we got energy. We have free energy. We have Gibbs free energy. Sometimes some books call it that, but really it should be maybe called free enthalpy. And then we have enthalpy. And you can look up a thermodynamic square, which talks about how to relate all those things with like energy, enthalpy, free energy, and free enthalpy arranged in a little 2x2 grid. And it's like, oh, if you go across the rows, you add PV. If you go down the columns, you subtract TS, like that kind of thing.
I see, yeah.
But all of that is to say you have an energy function, you have a function, energy, and you do Legendre transformations to them to swap which is the variable that you're having a differential of in your functions. Yeah. So sometimes those variables are called conjugate variables, which we use in other places in physics and math, right? Like conjugate variables are generally the variables on either end of a transformation. So like Legendre transformation has like P on one side and V on the other as like the variable of interest. But you can think of like a Fourier transform, the conjugate variables would be time and frequency,
right?
Stuff like that. And then to tie it back to like Hamiltonian mechanics, thermo, it's interesting. Hamiltonian mechanics is a Legendre transformation of your Lagrangian, and you change from position and velocity to a different variable pair of position and momentum, right? And they get flipped. But Hamiltonian, so that's the math. But the physics part of it is you're looking at a certain type of like differential geometry, which is called symplectic geometry. Is like the underlying mathematical principles that are happening there. You're like doing calculus on an abstract multi-dimensional space, but it's always an even dimensional phase space. It's like the physics that we're working in Hamiltonian mechanics. And it's interesting that there's like different rules for geometry when you have an even dimensional space is a symplectic geometry. But in thermo, we always have an odd number of variables because that energy in this example is unpaired. And so when you have an odd number, it's called a contact geometry. It's a different, instead of symplectic geometry. So symplectic is even dimensional, contact is odd dimensional.
Because you can't just call it even dimensional and odd dimensional.
Yeah. And Hamiltonian mechanics is even dimensional phase space. Like you're working in this like space that spans, it's like has a whatever hypervolume, if you want to call it that. But in thermo, we're working in hypersurfaces. We're kind of looking at like places where the energy is constant and then looking at the hypersurface within that odd dimensional space. where that's true, which is kind of an interesting way to think of it.
Yeah, some sort of like contour, sort of.
Yeah, exactly. So yeah, imagine like you live in a three-dimensional space, but then put a sheet running through your room. That's a surface. And you could say that's the sheet of constant energy and do physics on that. In thermodynamics, you're looking at this weird, abstract, odd dimensional space, but putting a sheet through it and looking at, constant energy and doing thermophysics on that. Good?
Yeah. Yeah. So we got all the, I don't know where we're going with it, but yeah, I mean, I feel like this, for me, this is usually as far as I follow easily in thermo. I'm like, okay, I don't know why we're doing these things. Now I know why, because we're trying to keep particular things constant. That helps a little bit.
Right.
But yeah, like mathematically, I follow. Well, the one thing that always got me, and we don't have to talk about this, I don't think, but it still kind of gets me. So it's the difference between doing math as a physicist and doing math as a mathematician. Is I maybe I shouldn't have listened, but I blindly just trusted my math teachers who said writing something like DE by itself is meaningless. It's stupid. Don't do it. It has like there is no point to doing that ever. Was what my calculus teachers taught me. You either have to have an integral sign there, or you have to have a D something by D something else. Otherwise, it doesn't make sense. And so, like, that always kind of bugged me when it came to this sort of stuff a little bit. But I recently started, I don't know, in the last couple of years, I did a little dive into differential geometry. Mm-hmm. And this is just a standard in differential geometry. They just like talk about D whatevers all the time. So I don't know, maybe I was lied to as a calculus student or whatever, but for whatever reason, that was a big trip up for me as a student learning this. Was like, okay, I thought we couldn't do this. Why are we doing these just a differential part? But either you give up and you just go with it, or you learn differential geometry. You're happy a little bit.
Yeah, I think I'll maybe agree with your math teacher. Not that I'm like an expert on that, but that Aviatin website has a lot to say about exactly what you just said. It goes into a lot of the like, here's what's right, here's what's wrong, don't do this, it's okay to do this. The DE is okay. And I think the reason it's okay is because what I said about like it being paired with a 1, kind of. What's not okay mathematically is the DQ and DW. Those are not allowed to exist in math and shouldn't be written in physics, which is one of the reasons this guy on the Aviatin website talks about, heat being, don't use heat. If you mean TDS by heat, say TDS. Don't say Q. Don't say DQ for TDS. And he goes into a lot of the math behind what's happening. And there's a difference between an exact differential and an inexact differential. And it has to do with us living in or working in thermodynamics with these like multi-dimensional spaces that aren't, basically, if we're taking a derivative, we have to say which direction we're taking the derivative in. And if we say TDS, that's a direction of S changing. But T is just constant, coming along for the ride, right? There's a way to think of it.
Yeah.
T is not constant. I shouldn't have said that. But like you could talk about the differential operator D acting on S, the entropy, but not T. And if you have a product of two things like that, you can't make them be equal to D any individual thing. There's no DQ that equals TDS because we have two different variables. And we need to, if we said DQ, we would have to say, okay, which direction? But there's not enough information in the Q really to define that. Q depends on the path we're taking, and the information isn't given by the function or the term DQ.
Gotcha.
You can work through a Q, like a heat of a process, by doing an integral around a path. But yeah, his argument is like, don't even talk about that. Just talk about that. If you mean TDS, just do TDS. like do the math with TDS. Same thing for work with PDV. So D energy, I think, is allowed. D heat and D work are not allowed. He has I wish I could find this. He goes through the definition of entropy in terms of dq. Like if you learn entropy thermodynamic wise in like your undergrad physics textbooks, they're talking about they say something like ds equals dq over t, right? Mm-hmm. And so he talks about how it was originally the definition of entropy, but like the way it was done was so convoluted, and now we have StatMech to like clarify what was actually happening underneath it all. See what his prescription was. He had like a nice bullet pointed walkthrough. Yeah, this is it. Okay. He has a section called thermodynamic paths and cycles. If you scroll a bit, there's a moment where he says, here's what entropy used to be defined as, and it's bonkers what the like roundabout way to get an answer for entropy was.
I like his
So section 813, converting out of state functions to state functions. So he says, so people were able to calculate the entropy anyway, meaning like without like really knowing what it was. Like modern thermodynamics, we define entropy in terms of probability of microstates. Back in pre-modern times, before like 1898, people had no understanding of microstates, but they were still able to calculate entropy in simple situations. And he's like, this is how they would do it. Build a reversible heat engine. Measure the heat along the path that the heat engine takes, along some path, as a function of arc length of that path. So like you have some space and the heat is some function of arc length around the path. So that is, measure the heat absorbed by the engine as a function of arc length as the engine goes through its cycle along the path gamma. It makes up a path. So with your reversible heat engine, you have a path and you measure heat. Differentiate that amount of heat with respect to the arc length. Multiply that by 1 over the temperature and integrate that. So you differentiate with respect to arc length, do a multiplication of 1 over T, and then integrate with respect to arc length. That's your entropy. So he's like, there's this huge roundabout way of calculating entropy. It used to be the definition of entropy before we knew like the StatMech part. And it's a mess. Don't do it. Don't try it. Yeah. But again, this is his explanation of why dq doesn't make sense. The like d operator acting on q is like kind of like a gradient, but it's like something that fundamentally can't be a gradient. Like you have to define the path of like where you're taking the derivative. Q depends on the path a lot. So yeah, usually the path, like usually the gradient, if you think of like force, right? Like du, like the gradient of some potential force. You're talking about like what's the direction of the steepest descent? It's negative del potential energy.
Right.
So what's the direction that's steepest descent happens? But you can't do that with Q because Q really depends on which direction you want to take a step in. And it's not always the steepest descent like it is with like force being defined to be that.
Right.
So like you can't really write dq anything.
Gotcha. So yeah, if your variable depends on where you're going, then you can't know ahead of time where to go because it's going to change.
Right. He's like, you can do it if you define your path ahead of time and you work only along that one path and you're taking differentials of the arc length around the path and you integrate with respect to the arc length at the end. It's like, that's how they used to do it. He's like, just don't do it. Just work with TDS. We know what S is now. We have a well-defined version of S. That's it. Yeah. And he has probably a few thousand words expanding on why you shouldn't use DQ.
That's I'm going to read that a little bit more, I think, at some point.
I really like this website. I like the way he outlines stuff. And it's like a good jumping off point too of like, I'm like, oh, I don't know that field of math or physics. And he like connects to stuff and you go and read more and you're like, oh, that's cool.
Yeah. I remember you, one's asking me about wedge products. I think that's how you told me about this site.
Yep. Yeah. If you look at, is it that page? The figure at the very top of that page, the thermodynamic paths and cycles. The first figure is a PV diagram.
Yeah.
And you can see how there's like the white lines and the green lines. Those are like, I think he defines them. Those are entropy and temperature, lines of constant entropy and temperature inside a PV graph. I wanted to highlight that, and maybe people listening have done this. P and V you can draw as like orthogonal coordinates, like X and Y on a graph, and then you throw down the other variables, temperature and entropy, and they're not orthogonal. They're not like a Z direction, like out of the page or something. They're like, they depend on the other variables and they cross each other and they're curved. All that to say, when you're doing thermodynamics, you're working with these variables that are like not nice, not well behaved. In particular, there's no definition. There's no way to define our dot product between like directions. There's no direction of stuff except to say the direction of constant entropy, for example, is like one of those sweeping lines. But you can't just say like a vector written in like 1, 1, 4 or something like that. Like you could in an XYZ three-dimensional system.
To move in a direction of like, that would just say, okay, go in this direction constantly. But we have to always, we're on a surface, so we have to like be traveling awkwardly on that surface. We can't, it's like walking on a mountain versus walking on a flat surface type of thing.
Right. Yeah. Yeah. And I think that's one of the reasons why thermodynamics is so hard, is because we're so used to X, Y, Z as like the three variables that a function might depend on. And they're all rectilinear, orthonormal. Like you can define your basis really nicely. You have inner products. But thermodynamics just doesn't give you that. You just have crossing variables that depend on each other in like a odd dimensional space, usually 5-dimensional space. It's just weird. It's just a weird system to work in. And you're trying to do like differential geometry in it. Is like the underlying math of what's happening. So you just it gets messy, and like you make hand wavy arguments for things you don't really know why. And it's such a huge leap in the math to like grasp what's actually happening underneath it all, that we just don't do it.
So that's what we're going to talk about then.
Yeah, I think moving forward, if we do more thermo stuff, is I want to dig into entropy and definitely stat mech and like where to build off of that. But as far as thermo, I don't know what else is there. What else is there in thermo? I know there's a hell of a lot more. But
I mean, I think one thing that would be interesting to talk about is just kind of like, for me at least, what are the uses? I mean, obviously, I feel like I've only ever heard engines. You use this for an engine, but I think there's a lot more types of engines than what we're used to thinking about, and B, just what other, why do people need this sort of physics in their life?
Okay, I have some thoughts, but we don't have to get into it now. But yeah, that could be interesting. Yeah. I know what you mean, though. Like thermo, quote unquote, engines get caught up or get brought up as kind of this abstract concept when talking about life. But yeah, I'm trying to keep it separate from stat mech. Like, what else is there in thermo that's not stat mech? And I think you're hitting on something where like engines as an abstract topic are the like driving systems of like solar power, like fundamentally something like that. Like you don't need stat mech to get into like what's happening thermodynamically with like the sun as like a heat source and like generating electrical work to charge a battery or something like that.
Yeah, I mean, I can talk to one of my coworkers too. She is working on building a DNA engine, actually. And so she might have some thoughts or things to say.
Yeah. Yeah. And yeah, I think the concept of heat engines can get abstracted away from like literal pistons and like trains and be thought of like things can be considered in terms of heat engine physics in ways that we're not usually used to seeing and like thinking about like life. I said that earlier, like I'm meaning cell growth and like photosynthesis and yeah, early molecules finding it energetically and entropically, is that the right word? Beneficial to just reproduce.
Right.
There's like ways to think about that kind of stuff that I'm not totally obviously 100% knowledgeable of, but I know people think about things in that way.
Yeah. Yeah. So I think like either learning about that or talking to some people about that would be neat.
Yeah. A popular scientist, Sean Carroll, I'm sure you know who he is. You've met him or saw him in a talk or something.
Yeah.
I think we've talked about him before. He has a lot of thoughts around this in his books. I might read one of those.
He one of the things that he talks about in, I forget the name of the book, but one of his latest books, pretty much, it's a book saying that we're pretty much done with physics. It's a little sad. He pretty much goes through and says like, the physics for anything that you will experience ever in your normal day-to-day life, we have explanations for all of that pretty much. But he talks about, one of the things that he talks about that's interesting is like emergent properties, which are these properties of things that don't exist in a simple form, but when you develop a complexity of some sort, you get these new kind of properties out. And like kind of the easy one to talk about is like temperature. Like it doesn't make a whole lot of sense to say like, what is the temperature of this atom, of a single atom? But when you get like your collection of atoms, your Avogadro's number, that collection now has the property of temperature, which is an emergent property that like we didn't really necessarily expect. And I think he talks about some stuff like that in some of his books. That's kind of that I found interesting.
Yeah. Cool. I'm going to dig into a Sean Carroll book. I think The Arrow of Time is the one I'm thinking of. That's like a lot of entropy talk.
Oh, that sounds like it is.
Yeah. I'll just finish with, we got off of the nuts and bolts part of stuff, but we were talking about it earlier. Those energy-like functions, I think you talked about it too, is like, they're called potentials sometimes, like thermodynamic potentials. And I think that was another place of confusion. So just to clarify, the enthalpy, free energy, free enthalpy, those are like potentials that are kind of like energy. They're not exactly. So yeah, when people talk about thermodynamic potentials, that's what they're talking about. Cool.
That was a good refresher.
Thermo overview. Yeah. I'm excited to, talk more about it. And do StatMech. I always love StatMech.
I want to love StatMech. Cool. All right. For me with StatMech, one of the things I thought was frustrating with StatMech was not only are you learning like this new form of physics to you, but a lot of times like you've never learned statistics really. Like you know what an average is, and like kind of a standard deviation, but then it took me a long time to grasp the idea that an average can be thought of in terms of probabilities. Like that was
we're used to all probabilities being, or all possible outcomes being equivalently possible. Like rolling dice is like how we're taught probabilities. But then, you have to think about like, well, what if it's more likely to get a 1 than a 6? Because it's not a perfect die.
Yeah,
like
exactly.
Yeah.
And I mean, it becomes really clear, but once you've like done it and thought about it for a long time, but like in trying to learn it, it was like I was trying to learn one thing to explain another thing. Yeah. And I didn't have a good grasp on the first thing, so it made the second thing even harder.
Right.